Welcome back to AI Paper Podcasts. Today we're diving into a really interesting one, supervised reinforcement learning. From expert trajectories to stepwise reasoning.
Yeah.
And its core insight really gets at a huge problem for LLMs tackling those hard, multi-step reasoning tasks.
Exactly. I mean, standard outcome-based reinforcement learning, RLVR, it just fails, often spectacularly on these difficult problems.
Why? Because the successful solutions are just too rare.
Pretty much. The model almost never gets it right, so it gets zero positive feedback. It just never learns the crucial intermediate steps.
Right. And then on the other side, you have supervised fine-tuning, SFT. But that's too rigid, isn't it? Forces this token-by-token imitation.
Yeah, exactly. It makes the model overfit these long, specific demonstrations, and it really limits how well it can generalize later.
So this paper introduces supervised reinforcement learning, SRL. And the big idea here is reframing the problem.
Totally. It sees problem solving as the sequence of logical actions, and then it gives dense stepwise rewards based on how similar the model's action is to the expert's action at that specific point.
So it's like getting partial credit for showing your work, even if the final answer isn't quite there yet.
That's a great way to put it, and the results are pretty stunning. SRL alone did much better than the baselines.
But the killer combo was SRL then RLVR, right?
Yes. That sequence achieved the highest performance. It actually allowed smaller models, like 7 billion parameter ones, to learn tasks that were basically intractable before.
Okay, that's the hook. If you're working on reasoning in LLMs, this is a big deal. So let's unpack how they actually built this SRL approach.
Yeah, absolutely. To really appreciate SRL, you first have to grasp just how bad the existing methods are for these complex tasks, especially with, say, smaller open source models.
Right, they hit a wall. And that wall seems to be RLVR reinforcement learning with verifiable rewards. It sounds good, but it relies on that final verifiable outcome.
Correct. Was the final answer right? Yes or no? That's the signal.
And on hard problems, what the paper calls gardeners, the model's success rate is practically zero.
So no positive reward signal, ever. Or, so rarely it doesn't matter. The training signal is just incredibly sparse.
Which leads to instability in training, right? Like if you make one small mistake early on.
The whole thing gets derailed. And the model gets a negative signal for the entire attempt, even if, say, 90% of the reasoning steps were actually solid.
That makes it basically impossible for smaller models, like the 7B ones they tested, to learn these kinds of tasks using standard RL.
Definitely. So then you think, okay, what about just imitating an expert? That's SFT, supervised fine-tuning.
Which uses next token prediction. Good for some things, like basic style transfer or knowledge distillation.
But it forces this super rigid token-level mimicry. The model becomes a parrot.
And for long, complex reasoning chains, that rigidity kills generalization. They even showed this empirically, didn't they?
They did. With the Quen 2.5 7B instruct model on their hard math dataset, S1K, using SFT actually made the model worse than the base model.
Worse? Wow.
Yeah. And there are two big risks here. One is overfitting to the expert's specific solution path, leading to shallow reasoning. It looks like it's reasoning, but it's just memorizing.
And the other risk?
They call it teacher hacking. The student model learns to perfectly replicate the teacher's specific flaws or weird formatting quirks instead of the underlying logic.
Like learning the professor's typos instead of the grammar rule.
Exactly. So the expert's trace becomes this hard ceiling on how well the student can ever perform.
Okay, so we got RLVR failing because rewards are too sparse, and SFT failing because imitation is too rigid, a clear gap.
And that's precisely where supervised reinforcement learning, SRL, comes in.
Its big shift is viewing problem solving not as generating one big blob of text,
but as a sequence of decisions, key logical actions.
And these actions depend on the domain, right? Like an algebra step in math or a command in software engineering.
Exactly. It's the critical, verifiable step at that point in the process. For their software work, it was things like a bash command or a specific file edit.
And how do they set up the training data?
It's quite clever. They take a complete expert solution with, let's say, the nuller steps. They turn that into one-on-one partial examples.
Okay.
So for each step cover, the model sees everything up to step k-dollar, and its job is just to predict the next logical action, seek dollar.
Got it. And they use that interesting structure with the think tags.
Yes, that's crucial. The model first generates its internal reasoning, its plan, inside think.think tags. Then it commits to the external action, usually in a separate tag-like solution or just the raw command.
And the reward It only looks at the action, not the thinking part.
Exactly. The reward calculation is based only on the logical action output, not the monologue inside the think tags.
But wait, if the thinking part isn't rewarded, couldn't the model just generate garbage thoughts as long as the final action happens to be right? Why even have the monologue?
That's a fair question. The monologue is still essential because it's the planning space. By separating the planning, the thinking, from the part that gets the reward signal, the action you give the model flexibility,
Flexibility how?
it can develop its own internal reasoning style.
Yeah.
It's not forced to mimic the expert's thought process token for token like in SFT. It just needs to figure out how to arrive at an action that matches the expert's next step.
Ah, I see. So it promotes better generalization because the model learns how to plan, not just what plan to copy. The reward guides the outcome of the thought, not the thought process itself.
Precisely. It ensures the external strategy aligns with the expert, but preserves that cognitive freedom internally.
Okay, that makes sense. Let's talk about that reward. It's dense, stepwise, constant feedback. How do they actually measure the similarity between the model's action and the experts?
They use a similarity ratio. Let's call it the stepwise score, $2. It's like, yeah, getting partial credit. If your algebra step is 90% similar to the correct next step in the expert trace,
You get a 0.9 reward for that step.
basically, yes. They use Python's difflib sequence matcher to calculate it. The formula is 1RL frac 2MT, where $1 is the number of matching elements, and $2 is the total number of elements in both sequences combined.
So it's a smooth, continuous signal, not just right or wrong.
Exactly, which really helps stabilize learning. And importantly, if the model messes up the format, like forgets the solution tag or outputs something nonsensical, it gets hit with a penalty, a -1 reward.
Okay, great dense reward structure. But they still needed dynamic sampling, DS, which comes from RLVR methods like DAPO. Why add that if the rewards are already dense?
Right, it seems counterintuitive, but it gets to a subtle point in RL optimization. Even with these nice, dense, stepwise rewards, you can still run into situations where a batch of rollouts provides almost zero learning signal.
Meaning the model is generating attempts, getting scores, but the training algorithm can't learn anything useful from them.
Exactly. This happens if, for a given problem, all the sampled attempts, rollouts, end up having very similar reward scores. There's near zero variance.
And if there's no variance?
The advantage estimate, which tells the policy how much better one action was than the average, becomes tiny or zero. No advantage means no gradient, no policy update. It's wasted computation.
So dynamic sampling just filters out those batches where nothing useful can be learned.
That's the idea. It ensures the model focuses its updates on samples where there's actually a meaningful difference in reward scores between the different attempts, indicating a clearer path towards improvement.
And the paper showed this wasn't just theoretical. It actually helped.
Oh yeah, significantly. Dynamic sampling gave a solid performance boost in their math experiments, lifting the average score on one metric from about 24.7 to 27.6. It's a necessary piece for stability, even with SRL's better rewards.
That really highlights the complexity. Okay, and they also compared this multi-step SRL approach to simpler reward schemes, right?
They did. They tested against just using the final answer reward, like standard RLVR, and also against something they called a holistic sequence similarity reward.
Holistic, so like comparing the entire generated solution to the entire expert solution in one go.
Exactly. It gives a single similarity score for the whole thing, still using sequence matching, but without the step-by-step breakdown.
So that isolates the benefit of sequence matching itself, but removes the granular stepwise guidance. What was the outcome?
Well, the results in their Table 3 were pretty clear. The holistic similarity was better than just the final answer reward. So guiding based on the sequence helps.
Right.
But the multi-step granular guidance of SRL was markedly better than both across all their benchmarks. That step-by-step partial credit really seems to be the key difference maker.
Makes sense. Okay, let's get to the main results on that tough S1K math data set using the Quinn 2.57b model. This is where SFT actually hurt performance, remember?
Right. So SRL on its own gave a substantial boost, about 3.0% on average over the standard RLVR baseline. It could actually make progress where RLVR stalled and SFT failed.
But the best result came from cheating them together.
Yes, the sequential approach. Train with SRL first, then fine-tune further with RLVR. That pipeline got the best overall performance, a 3.7% average improvement over the base model.
And that was just using 1,000 training examples. That's pretty data efficient.
It is. It suggests SRL is a really effective way to initialize the model's reasoning capabilities. It learns the robust intermediate steps with SRL's dense guidance.
And then RLVR comes in at the end to polish it, focusing purely on getting that final answer correct.
Exactly. Structure first with SRL, then optimize for the final outcome with RLVR. Seems like the best of both worlds.
What I found really cool, though, wasn't just the scores, but how SRL changed the way the models reason. They talk about emergent interleaved reasoning.
Yeah, that's fascinating. Instead of just writing one big block of thought at the beginning, the models started doing different things.
Like what?
Well, sometimes they still did upfront planning, which is fine. But other times they'd insert new planning steps or little think monologues mid-solution. Like they'd get partway through, realize something, and recalculate or adjust their strategy on the fly.
That sounds much more like how a human might work through a problem.
It does. And the third pattern they saw was reflective verification.
Checking their work before finishing.
Yeah. The example in the paper is great. The model solves for a variable, but before just stating the final answer, it inserts a quick thought like, think. Let's just double check this by substituting it back in. Think.
That's a huge step towards making these models more trustworthy, not just more accurate.
Absolutely. And importantly, they checked if this was just because the models were writing more.
Right. Is it just getting better scores because it's more verbose?
Nope. They looked at the distribution of reasoning lengths, figure 4 in the paper, and found it wasn't significantly different between the base model and the SRL-tuned model. The improvement seems to genuinely come from better planning and higher quality reasoning steps, not just more words.
Okay, so it works great for math, but they also showed it generalizes, right, to software engineering.
They did. And software engineering agents are a tough case for standard online RL because verifying if a code change worked can be slow, the context is huge, and there's lots of latency interacting with real environments.
So how do they apply SRL there?
They took another Quen model, the coder version, and fine-tuned it using about 5,000 expert agent trajectories. These were generated by Claude Sonnet, performing tasks like fixing bugs.
And the actions in this case were actual commands the agent would issue.
Exactly. Things like git checkout, specific file edits using sed or editor commands, running tests, anything the agent could actually do in the environment. This broke down into about 134,000 stepwise training instances.
And the results on SW Bench.
Really compelling, especially in the Oracle setting where the agent is told which file needs editing. SRL got a 14.8% task resolve rate.
How does that compare?
That was a 74% relative improvement over a strong SFT baseline called SWE Gym 7B, a massive jump.
Wow. Okay. So SRL really seems to provide that crucial fine-grained multi-step guidance needed for complex interactive tasks like code repair. It took a relatively weak agent and made it much more capable.
Yeah, it potentially changes the game for building more affordable, reliable AI agents for these kinds of real-world software tasks.
So wrapping up, supervised reinforcement learning looks like a genuinely robust and generalizable framework. It uses that dense, step-level feedback to make progress on hard, multi-step problems, where the sparse rewards of normal RL just don't work.
And it neatly bridges that gap we talked about. It's not as rigid as pure imitation learning, but it avoids the instability of pure outcome-based RL.
The authors did mention a couple of prerequisites for SRL to work well, though.
Right. First, the base model needs some fundamental instruction following ability. SRL isn't magic. It builds on existing competence.
Makes sense. And the second?
This is the more interesting one for future work. The way you decompose the expert solution into steps has to be good enough that the model can actually achieve good rewards with certain probability. The decomposition itself matters.
Ah, so that really puts the spotlight on how we design those expert actions and break down the tasks. If we adopt this SRL framework more broadly, maybe the next big challenge isn't just bigger models, but figuring out the best way to define those intermediate verifiable actions for even harder, maybe less structured problems.
Exactly. The quality of that step decomposition, that human insight into structuring the task, could become the critical design choice for unlocking the next level of reasoning in these models, especially the smaller, more efficient ones.
A fascinating thought to end on. How do we best teach the steps? Okay, that's all the time we have for this AI Paper podcast. Thanks for tuning in.